Hi everyone, myself Sampurna Lakshmi, Assistant Professor in the Department of EIA. Today we'll see that pass transistor logic and transmission gate logic in the VLSI design. So actually we have CMOS logics where we can use both the PMOS transistors as well as the NMOS transistors to implement all the combinational circuits and logic gates. Where two transistors, we have to use compulsory of the two transistors of PMOS and NMOS. Because of that, some of the power constraints are there. That is the reason we'll use either of these pass transistor logic or of the transmission gate logics in place of CMOS logics in order to reduce the power. At least if we are able to implement some of the applications with this pass transistor logic or with the transmission gate logic, we'll be able to get some of the efficient applications, like some of the efficient power uses. So in generally, pass transistor logic is used for the applications of ROMs, PLAs and multiplexers. So let us see what is a pass transistor logic. So this pass transistor logic can be implemented either of the NMOS transistor or of the PMOS transistor. Any single transistor is sufficient. So let us see here what does it mean. So it will be having two terminals. One is input terminal and output terminal. So 3 terminals, one more is gate terminal. So the data from input is transferred to output with the help of gate signal. So if you are giving the gate signal, then only the input will be transferred to the output. If the gate signal is not there, then the data will not be transferred. So here, if it is a NMOS transistor, you should give a gate signal with the positive voltage. If the PMOS transistor, you should give a gate voltage as the negative voltage. The reason behind that is, for the NMOS transistor, it requires a positive threshold voltage to get it on. For the PMOS transistor, it requires a negative threshold voltage to get it on. So here, the positive threshold voltage is considering as a logic 1, the negative threshold voltage is considering as a logic 0. So behind that, based upon that, we are saying that the PMOS transistor is on for logic 0, the NMOS transistor is on for logic 1. So here, if we are saying that if the gate signal is, this symbol is stands for logic, this symbol stands for NMOS. So here, if I am giving gate as a logic 1, so if I am giving input as a logic 0, because of this gate signal as a logic 1, the output will be logic 0. That is, whatever the input data I am giving at the input, the same thing is transferring to the output because of the logic 1. So if I am giving at the input as a logic 1, this data will be transferred to the output, the similar of logic 1, whenever the gate signal is of the logic 1. This is the pass transistor of NMOS type. So if we are considering as the PMOS, for the PMOS transistor, the gate signal you should give logic 0. Why? Because it requires a threshold voltage, negative threshold voltage. That negative threshold voltage is considering as a logic 0. So this logic 0, whenever the gate signal is a logic 0, the input is transferred to output. So if you are giving the input as a logic 0, output is logic 0. If you are giving input as a logic 1, output is logic 1. In that way, we are treating this as the pass transistor logic. So whenever we are considering these conditions, we have some limitations and we have some constraints. Let us see what are those limitations. So we have some conditions like a strong 1, weak 0, strong 0. Strong 1 stands for if the voltage is in between the 4.5 volts to 4.5 volts to 5 volts, then it is strong 1. If it is below the 4.5 volts and if it is up to 3.5 volts, then it is weak 1. And then if you are considering strong 0, the voltage should be from 0 to 0.5 volts. Then the weak 0 stands for 0.5 to 1.5 volts. In some cases, the negative voltage is also considering as strong 0. So we have like statements of the two statements corresponding to the NMOS as well as to the PMOS. So one statement is like the NMOS pass transistor passes strong 0 but weak 1, And one more statement is like the PMOS pass transistor passes strong 1 but weak 0. Let us see that the reason behind that. Why the NMOS pass transistor passes strong 0 but weak 1? So we are saying that the NMOS transistor will give the gate voltage of the VGS and then will take as V in and will take as V output. So in this one we can say that the V output is equals to VGS minus V threshold. V output is equals to VGS minus V threshold voltage. So some threshold voltage is subtracting from the gate to source voltage, which is causing a degradation in the voltage level of 1. That is the reason it is of the weak 1. But if you are considering the strong 0, whenever it is 0, some threshold voltage, because of the threshold voltage, it is going below the 0. That is the reason it is a strong 0 but weak 1. This statement is only because of the constraint of the threshold voltage. Let us see one more statement which is giving like why the PMOS transistor is passes strong 1 but weak 0. So we are taking that similarly as we have seen in the previous case of the NMOS transistor. Let us see for the PMOS transistor. So here this is V input and this is V output and this is VGS. So in this, if we are considering the equation for output, V output equals to VGS minus V threshold, but for the PMOS transistor, it is always the negative, threshold voltage is a negative, that is the reason minus of minus threshold. Then it becomes as VGS plus V threshold. Then because of this condition, always some voltage is greater than the input voltage whatever you are giving, that is causing to strong 1 but weak 0. So this is the justification for getting a strong 0, strong 1 and weak 0 for PMOS transistor and strong 0, weak 1 for NMOS transistor. These two are the conditions while taking the pass transistors. So if you are implementing any of the circuit with the NMOS transistors, any of the circuit with NMOS pass transistor, you should compromise for logic 1. If you are implementing any of the circuit with the PMOS transistor, you should compromise for the weak 0. So let us see how we can implement logic gates or any of the logic circuit by using this pass transistor logic. Let us see at least universal logic gates of the NOR and NAND gate. So let us take a 2 input NOR gate. We are considering this as the truth table. So 2 input we are saying that totally 4 combinations will get, and then for the NOR gate the output is whenever that any one of the input is 1, the output is 0. Remaining conditions, the output is 1. This is the truth table for 2 input NOR gate. So for this circuit, by using this truth table, we have to implement a pass transistor logic. So for that pass transistor logic, we have to consider a gate signal. Either you can take the gate signal as a or you can take the gate signal as the B. Let us consider, if I am considering gate signal as A. So if I am taking gate signal as A, if A equals to 0, my output is at A equals to 0, my output is reverse to B. If B equals to 0, output is 1. If B equals to 1, output is 0. That means my output is B complement. And then if A equals to 1, my output is, you can see here, if B equals to 1, irrespective of the B input, output is logic 0. That is the reason my output is logic 0. So if I want to implement with the NMOS pass transistor, if A equals to 0 means, if A equals to 1 means NMOS transistor will be on. And I have one more NMOS transistor. I have to take one more NMOS transistor and both are together. So if it is A and this is A dash. A equals to 1 means this is on. A equals to 0 means this is on. So here I am taking as the output. So if A equals to 0, output is B dash. That means the output is equals to B dash. So this is on for A equals to 1. For this the input should be B dash. If A equals to 1, output is logic 0. That means this should be logic 0. So this is the condition, or this is the implementation how you can done or how you can use. Otherwise in place of logic 0 you can go for a ground. So this is the how you can implement a pass NMOS transistor logic for 2 input NOR gate. Let us see how we can do with the PMOS. So in previous case we have taken the conditions. If A equals to 0, output is B dash. If A equals to 1, output is 0. So how you can implement with this PMOS transistor logic? A equals to 0 means our PMOS transistor will be on. So at A equals to 0 means directly will give A equals to 1 means directly you can give as A dash. Why? Because PMOS is on for A equals to 0 and this PMOS is also on for A equals to 0. That is the reason we are mentioning as A dash. So here it is B dash and here it is logic 0. In that way you can implement a 2 input NOR gate by using PMOS transistor logic. Previous case it is NMOS pass transistor logic with the control signal as A. So here we have considered a control signal as input A, control signal as variable A. Let us consider the same 2 input NOR gate with the control signal B. So here same truth table I am writing 0 0 0 1 1 0 1 1, and then here this is a truth table. So now I have the chances of taking as a control signal B. So if B equals to 0, at this condition I am comparing A with the output. So at the B equals to 0, my output is A equals to 0, output is 1. A equals to 1, output is 0. That means my output is reverse to A. And if B equals to 1, my output is irrespective of the input of A, whatever the input you are giving for A, but output is 0. So if B equals to 1, my output is logic 0. So you can implement this with either of the NMOS logic or of the PMOS logic. Let us consider, I am considering as the PMOS logic as 2 inputs, 2 transistors. So always the PMOS is on for B equals to 0. So directly B equals to 0 kabatti I am giving her B, and then here it is B dash. So at B equals to 0, output is A dash. At B equals to 1, output is logic 0. So in that way you can implement a 2 input NOR gate by using a PMOS logic as well as the NMOS logic at different control signals. So you can take the control signal either of the A or of the B. So similarly this is one more example of the NMOS pass transistor logic for multiplexer. So in this multiplexer, so for the multiplexer, we are considering the control signal as S. So if S equals to 1, output is B. If S equals to 0, output is A. Why? Because it is NMOS, that is the reason. NMOS is always on for S equals to 1. Well, here also NMOS is on for S equals to 1. That is the reason we are mentioning this as the S dash. So in that way we can implement a 2x1 multiplexer by using NMOS pass transistor logic. So you can see here also like 2x1 multiplexer with the PMOS. Let us see with the PMOS. So here S equals to 1, B. But here S equals to 0, B. So this will be, for S dash it will be B, for S it will be A. The same circuit with the PMOS logic. This is with the NMOS and this is with the PMOS. So in that way you can implement a multiplexer with either of the NMOS transistors or of the PMOS transistors. So next logic is like a transmission gate logic. So in previous logics we have to compromise at week 1 or week 0. So if you are taking that NMOS and if you are taking that PMOS, we have to compromise either of the logic levels. So in order to overcome that problem, we are taking this transmission gate. This transmission gate is the combination of PMOS as well as the CMOS. But even though the CMOS logic is the combination of PMOS and NMOS, there both are connected in series, but here both are connected in parallel. So the symbol is considering as this one, the transmission gate symbol, where it represents the two transistors. This is NMOS and this is PMOS. Both are shorted together. This is NMOS and this is PMOS. And then here the control signal C dash and C. Always we are saying that C equals to 1 NMOS is on, C equals to 0 PMOS is on. That is the reason. C equals to 0 is representing as C dash, C equals to 1 is representing as C, and then input is transferring to P. So here if C equals to 1, A equals to B. This is a logic behind transmission gate logic. So here we are combining both a PMOS transistor as well as NMOS transistor. Both will be always in the on condition. So for that we will use the different symbols here. These are the different symbols considering for the transmission gate symbol. You can use this symbol or you can use this symbol and you can use this symbol. If you are using this symbol, it will occupy the more space, and these two symbols will occupy the less space. So you can use any of the symbols of these two. So here you can take as the control signals and you can take as the input and the output. So this is C, means this should be compulsory C dash. So this is a transmission gate logic concept. So by using this transmission gate logic, we'll implement multiplexers, latches, flip-flops and other the logic gates. But by using these two logics like pass transistor logic as well as a transmission gate logic, large combinational circuits will not consider. Only some of the applications will be implementing by using these two logics. So let us see one or two examples of the transmission gate. So we have seen NOR gate for the pass transistor logic. Let us see NAND gate for the transmission gate logic. So here I am considering two input NAND gate by using transmission gate. For that, first we have to write the truth table. If any one of the input is 0, then output is 1 for the NAND gate. This is the truth table. So similarly, as we have seen in the pass transistor logic, here also we can consider any of the input as the control signal. So for the time being, I am considering A as the control signal. So if A equals to 1, my output is reverse to B dash, reverse to B. That is the reason I am taking output as B dash. Why? Because if B is 0, output is 1. If B is 1, output is 0. So my output is B dash. If A equals to 0, my output is 1 irrespective of the B input. So my output is logic 1. So for these control signals, for these concepts, I have to implement a transmission gate. So let us take, as two inputs are there, two transmission gates I have to consider. So the transmission gate symbols are like this. So here, if A equals to 0, output is logic 1. So I am giving here is the A, then obviously it should be A dash. Why? Because both should be reversed to each other, then only the data can be transferred from here to here. So if A equals to 0, this PMOS will be on. If A equals to 1, this NMOS will be, this NMOS transistor will be in on. So for this condition, the output is logic 1. For that you can take as plus 5 volts or you can represent directly as a logic 1. And then here A equals to 1. A equals to 1 means this should be A dash and this should be A. Why? Because this NMOS transistor is on for A equals to 1. At this condition, my output is B dash. In that way, you can implement a 2-input NAND gate by using transmission gate. The transmission gate means consists of both the transistors, PMOS as well as the NMOS. So this is implemented by taking the control signal as the A. In that way, you can implement the same thing by taking the control signal as the B. Like if B equals to 0, my output is logic 1. And if B equals to 1, my output is A dash. So for these two logics, you can implement the circuit by replacing A with B, B with A. In that way, you can implement any of the logic gates or simply a multiplexer or a simple combinational circuits by using a transmission gate logic. So this is one more example of transmission gate by using for the XNOR gate. So let us see how we can implement XNOR. So for that, XNOR truth table is, first we have to write XNOR truth table 0 0 0 1 1 0 1 1. So for this, this is XNOR, right? So here they have taken control signal as the B in the circuit. So if B is 0, output is reverse to A. So if B is 0, output is A dash. So if B equals to 0, this PMOS is on. That is the reason output is A dash. And if B equals to 1, output is similar to A. That is the reason if B equals to 1, so here represented as the B dash, where this PMOS is on for B dash and output is A. So I'll write here the control levels or control signals. If B equals to 0, output is A dash. If B equals to 1, output is A. So in that way, we can implement either of the XNOR or XOR or of the logic, all the logic gates by using this both transmission gate as well as the pass transistor logic. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.